Hello everyone, welcome back with me, Rafi. Here I want to describe again about computer architecture. Here I want to solve the several problems in a book that my lecturer already given. So let's get the ball rolling. Okay, the first problem. The first problem is a benchmark program is run on a 40 MHz processor. The executed program consists of 100,000 instruction executions with the following instruction mix and clock cycle count. And the question is determine the effective CPI, MIPS rate, and execution time for this program. Based on the table that we have instruction types, several instruction types like integer arithmetic, data transfer, floating point, and also control transfer. And also each of them has their value like instruction count and cycles per instruction. So the first thing that we should do is data breakdown in order to find the value of cycles. So how we can determine the value of cycles? We can do like multiply the instruction count with cycles per instruction. Here we have 45,000 instruction count and cycles per instruction is 1. So we multiply them and got 45,000 and so on. And we can do as integer arithmetic to data transfer, floating point, and also control transfer. After we got the cycles value for each instruction types, we can calculating the CPI. We can use the formula is for the CPI is instruction count multiplied with cycles per second and divided with number of instructions the executed program consists. So we have so we can answer using the formula like this. Each of the instruction count and cycles is multiplied here, and all of them is plus with each other. We get 45,000 plus 64,000 plus 30,000 and 16,000 divided by 100,000. 100,000 is the number of instructions the executed program consists. Here is 100,000 instruction executions. So we put the 100,000 over here. And finally, 155,000 divided by 100,000. So we got 1.55 for the CPI. The next is calculating the MIPS. The MIPS. So we have to break down MIPS formula. So for the processor time, the formula is T equal to LC multiplied by CPI and multiplied by T, where T is constant cycle time. So T also can be calculated as 1 divided by F. So MIPS can be calculated using formula MIPS F divided by CPI multiplied by 10, 10, 6. And based on the new formula, it can be calculated MIPS 40 multiplied by 10, 6, 1.55 multiplied by 10, 6. 40 divided by 1.55 and we got 25.8. So the MIPS of the program is 25.8. So for the next is calculating execution time using formula T equal to LC multiplied by CPI and multiplied by 1 divided by F. So for the answer is here. Using this formula, we calculated the execution time and got 3.875 ms, or it can be concluded that the execution time is 3.875. Okay, for the next problem. The question is, consider two different machines with two different instruction sets, both of which have a clock rate of 200 MHz. The following measurements are recorded on the two machines running a given set of benchmark programs. So the question is, determine the effective CPI, MIPS rate, and execution time for each machine. Comment on the results. Okay, so based on this table, we have to determine the effective CPI, MIPS rate, and execution time for each machine. And also we have to comment on the results. So using this formula, we can determine the value of CPI, the effective value of CPI, MIPS, and CPU for each machine. So here, sigma CPI multiplied by Li and divided by LC. So using this formula, we multiply each of the value of CPI and multiply by LE, which is 10 index 6. So, and divided by 8 plus 4 plus 2 plus 4, which is multiplied by 10 index 6. And we got 2.22. And MIPS F divided by CPI multiplied by 10 index 6. So we have 90 for MIPS. For MIPS for a machine. For the CPU, we also do the formula is L multiplied by CPI and divided by F. And we get 0.2 s or second. For CPI-B, we do the same with the CPA for machine A. So furthermore, we can get all of the CPI, MIPS, and CPU in B machine as in A machine. So for CPI-B, we get 1.92, and for MIPS for machine B, we got 104, and the last is CPU for B machine, we got 0.23, 23s. So the next problem is, early examples of CISC and RISC design are the VAX 11780 and the IBM RS 9000. Respectively, using a typical benchmark program, the following machine characteristics results. We got a table over here, and the final column showed that the VAX required 12 times longer than the IBM measured in CPU time. So the question is, what is the relative size of the instruction count of the machine code for this benchmark program running on the two machines? And what are the CPI values for the two machines? According to the table, we have two different processors, which is VAX 11780 and IBM RS 9000, which is each of them has different clock frequency, performance, and also CPU time. So here is the answer. The MIPS rate could be computed as the following, like MIPS rate divided by 10 index 6 equal to LC divided by T. Thus that LC equal to T multiplied by MIPS rate divided by 10 index 6. Now by computing the ratio of the instruction count of the IBM RS 6000 to the VAX 11780, which is X multiplied by 18 divided by 12 multiplied by 1 equal to 18x divided by 12x. So we got 1.5 for the value. And regarding the fact the VAX 11 divided by 780, the CPI equal to 5 megahertz divided by 1 MIPS equal to 5. So analysis regarding to the IBM RS 6000, the CPI is equal to 25 megahertz divided by 18 MIPS. So we got 1.4 for the value of the IBM RX 6000 RS. So the fourth part problem is 4 benchmark programs are executed on 3 computers with the following results. We have 4 program and 3 computer in this table. So the table shows the execution time in seconds with 100 million instructions executed in each of the 4 programs. Calculate the MIPS values for each computer for each program. Then calculate the arithmetic and harmonic means assuming equal weights for the 4 programs, and rank the computers based on arithmetic mean and harmonic mean. So the answer is like this. MIPS equal to LC divided by T multiplied by 10 index 6. Arithmetic mean RA equal to 1 divided by M sigma M RI. And harmonic mean is R8 equal to M divided by sigma M1 divided by R1. So by applying MIPS, LC divided by T multiplied by 10 index 6, which is we got 100 million divided by T multiplied by 10 index 6 equal to 100 divided by T. Therefore, the MIPS values are like this. According to those formula, I got several values for each program and each computer like this. For program 1 and computer 1, I got 100, and program 1 computer B I got 10, and program 1 computer C I got 5. Program 2 computer A I got 0.1. Program 2 computer B I got 1, and also program 2 and computer C I got 5, and so on. You can see on this table that I have created. And also for arithmetic mean and ring, I got like this. Computer A is 25,575 with which has rank 1, and computer B with arithmetic mean is 2.80 with rank is 3, and computer C is 3.25 which has rank 2. And also the harmonic mean I got for computer A is 0.25 rank 2, and computer B is 0.21 rank 3, and also computer C 2.1 and rank 1. So perhaps this is the last problem. The following table, based on data reported in the literature, HIT 84, shows the execution times in seconds for 5 different benchmark programs on 3 machines. We have a table over here, and the question is, compute the speed metric for each processor for each benchmark. Normalize to machine R, that is the ratio values for R are all 1.0. Other ratios are calculated using equation 2.5 with R treated as the reference system. Then compute the arithmetic mean value for each system using equation 2.3. This is the approach taken in HIT 84. And B is repeat part A using M as the reference machine. and this calculation was not tried in heat 84. And C is which machine is the slowest based on each of the preceding two calculations. And D, repeat the calculation of parts A and B using the geometric mean defined in equation 2.6, which machine is the slowest based on the two calculations. So here is the answer. Since we have the same instruction mix, that means the additional instructions for each task could be allocated appropriately between the instruction types. Therefore, the following table begotten is like this. For instruction type for arithmetic and logic, CPI as instruction mix is 1 and 60%, load store with change heat 2 and 80%, branch is 4 and 12%, memory reference with change miss is 12 and 10%. So the average CPI is 1 multiplied by 0.6 plus 2 multiplied by 0.18 plus 4 multiplied by 0.12 plus 12 multiplied by 0.1. So we got 2.64. Therefore, the CPI has been increased since the time for memory access is also increased. For B, MIPS is equal to 400 divided by 2.64 equal to 152. There is a corresponding drop in the MIPS rate. For the C, the speed up factor equals to the ratio of the execution times. The execution time is calculated as the following: T equal to T equal to LC divided by MIPS multiplied by 10 index 6 for the one processor T1 equal to 2 multiplied by 10 index 6 divided by 178 multiplied by 10 index 6, which is we got 11 ms. For the 8 processors, each processor executes 1 divided 1 8 of the 2 million instructions plus the 25,000 overhead instructions. Then the execution time T for each of the 8 processors is speed up equal to time to execute program on a single processor divided by time to execute program on n parallel processors. So we got 1 divided by 1.8. So the answer is 6.11. And the last is D. In fact, there are two inefficiencies in the parallel system. The first one is that there are more additional instructions which is added to coordinate between threads. The second one is that there is contention for memory access. Thus, none of the code is inherently serial and all of it is parallelizable but with scheduling overhead. It could be said that the memory access conflict means some extent memory reference instructions are not parallelizable. By depending on the information given, it's not obvious how to quantify this this effect in Amdahl's equation. Therefore, if it is supposed that the fraction of code which is parallelizable is f equal to 1, then Amdahl's law decreases to speed up equal to n equal to 8. Therefore, the actual speed up is only about 75% of the theoretical speed up. So, thank you for hearing my presentation. Hope you get my point that I have given to you. So that's all for me. My name is Rafi and have a nice day. Thank you.